Hello, geometry students. Welcome to Chapter 6, where we're going to be talking today. We're going to look at Lesson 611, that is specifically looking at congruent triangles. And so this chapter is we're going to talk about what makes triangles congruent, or how you know if two triangles are congruent. And then we're going to start to also not only be able to explain it, but put that explanation together we're going to start looking at proof. Okay? Mr. Kunin's quote of the day today: "You only fail when you stop trying." Are you trying to complete your practice to learn? Keep trying. Okay? Just keep working. Perseverance is kind of one of the things we're always looking for. Objective for today: I can identify congruent triangles by determining that triangles are similar and that the ratio of corresponding sides is 1. Okay? So we'll talk more about that as we work through the lesson today. But if we take a look, warm-up, I'm going to have you work through the warm-up here today if we take a look. So what I want you to do is go ahead and pause the video and see if you can do the warm-up. And then I will come back and we'll talk about the warm-up together here real quickly, and we'll go from there. Okay? So pause the video, give it a shot. Okay, welcome back. Let's see where we're at here on the warm-up. So part A, number 1A, I asked you to graph this line. It's already in y equals mx plus b form. And so if we take a look, the -1/2 is my slope. The +4 is my y-intercept. So if we're going to go ahead and we're going to graph this, that means we start with a point, y-intercept of +4, and then we use the slope to come up with other points. So I always put the negative in the rise. So I'm going to go down 1 and to the right 2 from my y-intercept. So down 1 over 2 would give me another point there. Down 1 over another 2 gives me another point. Down 1 over 2. Down 1 over 2. There's a whole bunch of points. I could go up 1 and over 2 if I wanted to, and just continue this pattern. Okay? And then we go through, and I missed most of the points, but you get the idea. There's the line that we're dealing with. Okay? So now I asked you to identify both the x and the y-intercepts. Well, first off, we started with the y-intercept when we were graphing. So that's the point 0,4. There's my y-intercept. Okay, y-intercepts are always when x equals 0, because that puts them on the y-axis. X-intercepts are always when y equals 0. And I did the slope enough where I went through, and if you notice, I ended up over here. Oops, I did this wrong, didn't I? I went down 1 over 2, down 1 over 2, down 1 over 2, and then I went down 1 over 1. That point should actually be over here at a +8. Missed it. That one should not be there. And so my x-intercept in this case is 8, 0. Other way that you could have found either of these, x-intercept is when y equals 0. So I could have plugged 0 in for y and solved for x. Or for the y-intercept, it's when x equals 0, which means I could have plugged in 0 for x and solved for y. So you can always substitute in 0 for each variable to find your x and y intercepts. In this case, it turns out that they were both nice points on the graph, and we got it. Okay? If we finish this problem off then, I asked you, what's the slope of any line parallel to this one? And if you remember, parallel lines means that you have the same slope. That is why they do not intersect. So in this case, slope of the line I originally had was -1/2. Therefore, slope of the line of any line parallel would also be -1/2. And the last part then, what's the slope of any line perpendicular to the given line? Remember, there's two parts to being perpendicular. You got to have opposite signs. Since this one's negative, I know the next line's going to have a positive slope, and it's the reciprocal, okay, which remember is when you flip-flop this. So since this is negative, I know this one's going to be positive, and the reciprocal of 1 over 2 is 2 over 1, which means 2 is the slope that I'm looking for, a +2. So any line that's perpendicular to this one would have a slope of 2. If we come down a little bit further, some of this more factoring type of problems that we have here. We talked about the factoring in this case. So let's go ahead and let's see what we can do on this one. So if we go through and we factor this, remember we start with factors of the first term. I'm going to start with 2x and 3x. If those two don't end up working out, then I'll come back and I'll do 6x and 1x instead. Okay. Then we go factors of our last term, which are either 2 and 2 or 4 and 4. I'm going to start with 2 and 2, see what happens. And then remember, we have to go through and we have to check the inside, which gives me 6x, and the outside, which gives me 4x. And from 6x and 4x, the question is, can I get this middle term of 5x? And in this case, the answer is no. There's no way from 6x and 4x, making them positive, negative, any of that, that's going to work out. So we go back, and since that didn't work, normally we would go through and we would flip-flop the two numbers, but since they were the same numbers, that means that's not going to work. So instead, let's go through and let's try 4 and 1. See if that works. Now we've got a 12x. Outside gives me a 2x. Unfortunately, from 12x and 2x, that's not going to work either. So now, here's where I'll go through and we'll try. Let's flip-flop let's go 1 and 4 instead, see what happens. This will give me a 3x. Outside gives me an 8x. And now, if we take a look, I need a positive 5x, which I can get if this is a positive 8 and a negative 3. And I know the signs have to be opposite because they need to multiply to be a negative 4. So we're in good shape here, which means this is going to be a minus sign, and therefore that's a plus sign. And now, if we finish this problem off, we factored it. Remember, we're looking for, a key word here is solve for x. Here's where the zero product property comes into play. Now we take the first factor, 2x minus 1, set it equal to 0, and solve. We're going to add the 1 over, divide both sides by 2, and I get x equals 1/2. There's my first answer. Then we take the 3x plus 4, set that equal to 0. And same thing, we're going to solve. So 3x equal to negative 4, divide both sides by 3, and I find out that x equals negative 4/3. There's my second answer. So there are your two x-intercepts in this case. Here's another one of those factoring ones. Again, you're going to keep seeing those over and over again as we work our way through that. Okay? Problem number 3 here, I'm going to go a little bit quicker through this only because we've spent quite a bit of time working on this. But if we take a look, we're going back to the last chapter. If 20 degrees is my angle, my reference angle, the 100 is your adjacent side. That's your adjacent leg. The x is the hypotenuse, and therefore, because we're working with adjacent and hypotenuse, that makes this a cosine problem. So we're going to take the cosine of 20 degrees over 1, equal to, by definition, adjacent, which is 100, over hypotenuse, which is x. And now we go through and we cross multiply. I get x times the cosine of 20 equal to the other diagonal of 100. X is not by itself, so I need to get it by itself, which means we need to divide out the cosine of 20. Those cancel, and now we end up with x equaling approximately, I know the answer is going to be more than 100 because it's the hypotenuse, so it's got to be bigger than the legs. And in this case, I'm not even sure on my calculator on here that I have that available. Well, we'll give it a shot. 100 divided by the cosine of 20 equals, there it is, 106.42, because we're going to the 100th place, and therefore that 7 tells me I need to round up. So 106.42 is your approximate answer on that one. And there we are. Okay. So we had right triangle trig one. This would be like a geometric connections problem on the next test. Algebraic, you will see one of these on the next test, I can promise you that. Okay, and then here's some more algebraic connections stuff as well. All right, so let's take a look. If we keep going, so the next question is why proofs in this chapter? Why are we doing that? So we're going to start off with baby steps. That's why these first two pictures are here. And the baby steps are, we're not trying to prove anything that's super, super big or super important. We're trying to prove that two triangles are congruent. So those are the baby steps versus doctors, nurses, things like that. They are always trying to go through and immediately on the fly trying to put together some logic of all right, here's what they tell us. Here's what the symptoms are for a person. Therefore, what does that tell us? What's the conclusion? A lawyer in this scenario, kind of the same idea. They're trying to go through and prove innocence or guilt one way or the other. Same things with police officers. They're constantly trying to figure out the clues and try to figure out what that tells them. Anybody that's in construction having to just problem solve is basically the idea. That's kind of what all these pictures are about. So if you take a look, Chapter 6 is about congruent triangles, but how can I use the information to construct arguments, justify those conclusions, and respond to any arguments that are presented by others? Okay? So if we take a look, Chapter 6, here it is, congruent triangles is the key idea. And if we go through and we take a look, we kind of already talked about this, so I'm not going to worry too much. We are only going to do the 6 ones in this chapter, along with some other stuff. So congruent triangles, if you take a look, in Chapter 3, you learned how to identify similar triangles and use them to solve problems. But what can be learned when triangles are congruent? In today's lesson, you're going to practice identifying congruent triangles using what you know about similarity. As you search for congruent triangles today, focus on what do I know about the triangles, how can I show that they're similar, and what's the common ratio? Those are 3 key questions that we're going to keep coming back to. So one thing I want you to come back to is this idea. If you remember back to the similarity concepts that we talked about, there were 3 ideas. There was angle-angle similarity. If the angles are congruent, you know the triangles are similar. There was side-side-side similarity, which meant if all 3 sets of sides were in the same ratio, same zoom factor, we didn't even have to worry about the angles. Then we knew they were similar. And the last one was a combination of the 2-side angle-side similarity. If 2 sets of sides are in the same ratio and the angles between are congruent, then we know that the triangles are similar. So just a quick refresher again, going back to Chapter 3, we're going to use these concepts quite a bit. Okay, so if you take a look at problem 6.1 here, they ask you to make a flowchart. There's our first proof that we're going to talk about, and we'll do that down below here, okay, showing that these triangles are similar. So if we start with that, the first thing that I'm going to take a look at is I'm going to use the side lengths here, okay? So for example, I'm going to start with AC. I'm going to start with what looks like the hypotenuse. I don't know if it is for sure, because notice I don't have a right angle, even though it looks like one. So I'm going to say the ratio of AC to EF. So here's my flow chart down here below. I'm going to say AC to EF. The ratio of those 2 sides, if we take a look, the ratio of those two, 7.5 to 7.5, those are in a 1-to-1 ratio. Okay, so that's what I'm going to put down. That's a 1-to-1 ratio. That is something I know. Second thing that I know, ratio of AB to DF. I know that is also a 1-to-1 ratio. So the ratio of AB to DF, that is, again, a 1-to-1 ratio. And finally, the 4.5s that we have here, the ratio of BC to DE. DE, there we go. That is also a 1-to-1 ratio, which means, remember, we came back up here and we had said that if side-side-side similarity means that if all 3 sets of sides are in the same ratio, we know that they are similar. So that's what this flowchart is saying right here. There's one set of sides and the corresponding ratio. There's a second set of sides and its corresponding ratio, and the third set of sides and its corresponding ratio. The reason these arrows are here is this is saying, all right, based on this information, what's my conclusion? Well, therefore, I know that we can conclude that these 2 triangles are similar. So I'm going to say triangle ABC, triangle ABC is similar to triangle. Remember, when you write a similarity statement, you got to match things up. So if we went AB, that means here we got to go FD. Okay, ABC is going to be FDE in this case, are the letters that have to match up. FDE. And in this scenario, what we're going to do is I'm going to put down, right below all the bubbles, I'm going to put the reasons down right away. So how did I know that this was in a 1-to-1 ratio? What I'm going to put right below here is I'm going to say that it's given Because it is. It's given to me in the picture, the actual side lengths. Same thing here. This is also given, that those side lengths were given to you in the picture. I didn't have to solve for anything or do any work. And same thing here. That is also given. Well, what's the reason? How do I know that these triangles are similar? That was our side, side, side similarity. We just proved that there's side, side, side similarity. So this is just a way, this is what's called a flowchart proof, and it's just a way to organize your thought process. So if we take a look back up here, we now made a flowchart. Question is, are these triangles also congruent? And I'm hoping that as you look at this, not only are these sides all in the same ratio, but because they're all in a 1-to-1 ratio, not only are they similar, that means they are also congruent. So in part B, are they also congruent? And the answer is yes. And the reasoning is it's the 1-to-1 ratio. If it was in a 2-to-1 ratio, now that means one triangle is twice as big as the other. If it was in a 3-to-1 ratio, then they're not the same size. 1-to-1 means they are not only the same shape, but also the same size. So now if you take a look at part C, notice it says, while the symbol for similar figures is this one little squiggly, the symbol for congruence is that same thing with an equal sign over there, over the underneath, excuse me. So how is the congruent symbol related, and why do you think they chose that? Basically, congruent means similar with equal sides. Similar shape, but equal side lengths. There's that 1-to-1 ratio. That's where the congruent symbol comes from. And so finally, part D then, Luis wanted to write a statement to convey that these two triangles are congruent. He started with CAB, but then got stuck because he didn't know the symbol for congruence. Now, can we write his congruent statement? And we absolutely can. So now if we take a look at this, rather than going through and saying these triangles are similar, I can write a congruent statement. I'll just do that right up here, up above, as like a separate problem. So if we say triangle CAB is congruent to triangle, and again, without even looking back at the picture, I'm going to use the letters. If it's CAB, that means over here it's going to be EFD, if we did that similarity statement. And there's your congruent statement right there. So now you have stated that not only are the triangles similar, they are also congruent. Right? So we've taken that step from similarity that we did back in chapter 3 to now congruence. The only difference is 1-to-1 ratio for the side lengths. All right, so let's take a look. Here's just some examples here that I want to take you through. So the diagrams below are not drawn to scale. For each pair of triangles, determine if they are congruent. If you find congruent triangles, write a congruent statement. If they're not congruent, then just talk about cannot be determined. So we're not going to do too much with the idea here so far of making a flowchart. You'll have a couple problems in there, your practice to learn. But the idea is whatever statements that you're saying is true goes in here, and the reason goes right below. Here's I stated this is true. Right below is the reason why. Okay. So in this case, I'm not actually going to do a flowchart or anything. I'm just going to try to figure out if these triangles are similar with a 1-to-1 ratio. So if we take a look at part A here, notice I've got one set of angles. And then if we take a look, I also know that this also must be a 90-degree angle. If that's 90, because the total's got to be 180, they're supplementary. So there's my angle. I know they're similar. So the question is, do I have anything in here that could show me a 1-to-1 ratio? And because this side right here is a shared side between the two, we know that that means that there is a 1-to-1 ratio in there. Okay, we're just looking for at least one piece to tell me that we have that 1-to-1 ratio. And so in this case, I can say that triangle, I'm going to go ABD, is congruent to triangle CBD. These are just reflections of each other is all that's going on. There's your two triangles. So now if we take a look at the next one, here's one set of angles. Okay, first one was angle-angle similarity with a ratio of 1. There's one set of angles. We got a set of sides that are congruent, so there's a 1-to-1 ratio. One other thing that I know is true in this picture is this side, again, is a shared side, therefore it's congruent to itself. And so if we take a look, there's my side angle side. And because they've got congruent side lengths, that means there's my 1-to-1 ratio. Here's also your side angle side. And because the sides are congruent, that's your 1-to-1 ratio. So once again, I'm going to write down triangle. This time we'll go DBC, congruent to triangle ABC. And there's your two congruent triangles on that one. So similar because of side angle side, but because we've got a 1-to-1 ratio between those sides, that's what makes them congruent. Similar with a 1-to-1 ratio. Let's take a look at part C here, same idea. If we take a look at this one, notice we've got parallel lines on this one, okay? And so therefore, we can mark some congruent angles in it. You should be thinking congruent angles on this one. So if we take a look, that means this angle E right here is congruent to angle B. Okay, those are alternate interior angles. Here's your letter Z right here in the picture. Okay, so those are congruent angles in this case. I also know that this angle is congruent to this one because of alternate interior angles. And I also know by default that these two are vertical angles, and therefore those are congruent. Now, what I want you to notice, and these markings are so important because a lot of times students will take a look at this and they'll say, oh, these are just two reflections of each other. Therefore, yes, they're congruent. But if you notice the markings, this angle is not congruent to that one. This is actually a rotation. So this 6 actually rotates over to that side, and this 4 rotates over to that side. This is a rotation, which means even though these triangles are similar because of angle, they are not congruent because they are not, the side lengths are not in a 1-to-1 ratio. So this one cannot be determined. At least not congruence, they can't. They are similar, we know that. But because the side lengths don't match up in your 1-to-1 ratio, that's why they're not congruent in this case. And finally, if you take a look here in part D, if we take a look at part D, what we're actually looking at here is two separate triangles that we're taking a look. So triangle number 1 would be this triangle right here. It's kind of overlapping triangles, and they're in two opposite directions. There's triangle number 1, which if you notice, you got 2 markings up here in this corner, and then 1 marking. So you got 2 congruent angles. Then if we take a look at the other triangle, which is right there, that's got 2 markings and 1 marking. So there's your angle similarity. So the question becomes, is there anywhere that we have a 1-to-1 side, a 1-to-1 ratio for the side lengths? And it turns out we do. This side right down here at the bottom, side AB, is a shared side between both triangles, so it's congruent to itself. So that gives you that 1-to-1 ratio, and therefore, ultimately, if I can say that triangle DAB is congruent to triangle, if it's DAB, okay, so I got to start with 2 markings, therefore CBA would be the one to match up. And there are your congruent triangles right there. Okay, so again, what you're looking for first is, are the triangles similar? Then you're trying to see if there's a 1-to-1 ratio. If it has both, then you know that they're congruent. If it doesn't have both, then they are not. Okay, all right. So if we keep going, here's exactly what I was talking about, methods in the math notes box. 2 figures are congruent if there's a sequence of rigid transformations. All that means is if I were to take like this triangle, for example, I can just do a rotation of this triangle. That's the rigid transformation that they're referring to. Okay, I can take this and rotate it so that it matches up perfectly with that one. And the idea is, here's your similar figures with a 1-to-1 ratio. That's what we're talking about. Okay, and you can always match things up from one shape to the other. All right, oops, I'm not going to go over that. So practice to learn for this lesson is the 611 practice to learn, 611 worksheet. However, you can skip problems 6, 8, and 6, 9. And we'll start class the next time I see you with any questions from the 611 worksheet. Hopefully this is making some sense. Good luck with everything. I hope you're doing okay. If not, send me an email and we'll talk. Otherwise, we can talk in class too. Okay? Talk to you later. Have a good one, everybody.